we were considering decidability results. If a problem has a corresponding language, then the problem is undecidable if the language is not recursive, but the language may be recursively enumerable or not recursively enumerable. So, we have seen that some are recursively enumerable, some are not even recursively enumerable. Look at this problem. Is L empty? Is L equal to sigma star? These problems are such that the corresponding languages are not even recursively enumerable. They fall outside the recursively enumerable sets. Is the language generated empty? Is the language generated is the language accepted by a Turing machine equal to sigma star? Is the language accepted by a Turing machine recursive? Is the language accepted by the Turing machine not recursive? Does it have just only one string accepted, or is the language accepted regular, or is the language accepted minus LU? You know what is LU? MW, M accepts W. Is it non-empty? These questions are not decidable, and also the corresponding language falls outside recursively enumerable sets. These properties of recursively enumerable sets are not decidable, but the corresponding languages, they are recursively enumerable, they fall within recursively enumerable. They are not recursive, but recursively enumerable. Is L non-empty, or does L contain at least 10 members? Is W in L for some fixed W? This is the membership problem. Membership problem for Turing machines is recursively enumerable but not recursive. For context sensitive languages, it is p space complete. For context free languages, it is order n cubed algorithm you have. Finite state automata, linear algorithm you have. Is L intersection LU not equal to 5? This is again recursively enumerable, corresponding language is recursively enumerable but not recursive. All these are undecidable problems, they are non-trivial properties of recursively enumerable languages. So, by Rice's theorem they are not decidable, but some are the languages. If you consider that language, what is that language? M, the Turing machines for which the language LM will satisfy this. Some are recursively enumerable, some are not even recursively enumerable. There is a theorem, Rice's theorem for recursively enumerable index sets, which we will not be considering now, that tells you under what conditions that language, corresponding language is recursively enumerable but not recursive. There are 3 conditions to be satisfied and so on. Next we go on to post correspondence problem, which is another undecidable problem. Generally it is called PCP. So, what is a post correspondence problem? This is again undecidable, we shall prove that it is undecidable. An instance of the post correspondence problem has 2 lists. It has got 2 sets of strings, W1, W2, Wk. One set is that, another set is x1, x2, xk. The same number of strings, the strings are different, okay, but the equal number of strings over an alphabet sigma. We will assume that sigma has at least 2 elements. If it has got one element, it is different, the problem will become different. It has got only minimum 2 letters, sigma has at least 2 letters. And you have 2 sets of strings W1, W2, Wk, x1, x2, xk. This particular instance of PCP, you say that it has a solution if you have a sequence of integers I1, I2, Im, each is between 1 and k, such that Wi1, Wi2, Wim is equal to xi1, xi2, xim. you concatenate them in this order Wi1, Wi2, Wim, the string which is formed is equal to the string formed in the xi1, xi2. The strings are taken in the same order. If this is possible, you call it, you say that this instance of PCP has a solution. If this is not possible, the instance does not have a solution. So, the question is, given two sets of strings, does it have a solution or does it not have a solution? This is an undecidable problem. We will prove that. Now, as an example, take these two lists. There are two lists, list A and list B. This has got 3 strings, this has got 3 strings. Does this have a solution? If it has a solution, it cannot begin with this 3, right, because the first symbol itself is different there. It has to begin with this or this. The probability looks like this is a better solution. So, if you start the solution, right, taking 2, the W string is this, the X string is this, right. Now, after concatenating, you must have the same string here and same string here. Okay. So, next you have a 1 1 1 here. So, it looks that better you take this here. So, you choose 1 now, next pair chosen is 1. So, you add a 1 here, this 1 is added here, that 1 1 1 is added here. Still they are not equal, they match up to this point, but they are not equal. You must have the same string in same W string and same X string. So, next again you choose 1, the same 1 here. So, 1 you have chosen, 1 1 1 here. Now, the X string is longer, right. Then if you choose 1 0 0 here, 1 0 0, that is 3, the two strings become equal, right. So, this instance of PCP has a solution, and what is the solution? 2 1 1 3 is the solution. Okay. 2 1 1 3, 2 1 1 3, 2 1 1 3 will be a solution. Any number of times you take also will be a solution, that does not matter. We take one, if there is one sequence which satisfies, that is okay. We stop at that stage. Okay. So, this instance of PCP has a solution, right. And what about this instance of PCP? You have two lists A, B, each having 3 strings. This is the W list, this is the X list. Okay. Let us see whether this has a solution or not. Now, the W string and the X string you have to form, you see that you cannot start the solution with this, because the first symbol is different. You cannot start the solution with this, the first symbol is different. So, if at all there is a solution, it has to start with 1. So, start with 1. So, in the W portion you have 1 0, in the X portion you have a 1 0 1. Now, in order to continue the solution, I must have the W string beginning with a 1. This symbol has to be 1 here, right, to continue the solution. So, I can have this or this, I cannot have this, right. So, if I cannot have this, suppose I take 1 0, then the B one is 1 0 1, there will be mismatch here. So, I cannot continue the solution with one, I have to use 3 only. If I use 3, I will get 1 0 1 0 1 1. The two strings match up to this point, but the X string is slightly longer. Now, the same situation has come. If I have to continue the solution, I have to again take 3 only, that is 1 0 1 0 1 1. Any number of times I can choose 3. The two strings will match up to a point, but the X string will be longer. One more 1 will be there, that will be always there. So, that instance does not have a solution. This does not have solution. This has a solution, which is 2 1 1 3. We have considered two examples, two instances of the post correspondence problem. We shall consider two more examples. Consider the following sets of strings. You have 4 strings and you have 4 strings in the X set. Now, does this instance of PCP have a solution? We find that 2 1 4 3 is a solution for this instance of PCP. As you see, starting with W2 and X2, you have this string, then proceeding with W1 and X1, you get this. Up to this point they are equal, but the first string is one symbol more. Continuing with the W4 and X4, the solution is this up to this point. Now, the lower string is one symbol more. Now, you have W3 and X3. Now, you find that you have the same string in W and in X. So, 2 1 4 3 is a solution for this instance of PCP. Let us consider one more example. Consider the following sets with 3 strings in W and 3 strings in X. If a solution exists here, it cannot begin with 3 because the first symbol is A here and the first symbol is B here. It cannot begin with 1 also because if you start with this, the first symbol is the same, but the second symbols are different. So, if at all there is a solution, it should start with 2. If you start with 2, we get this. Now, to continue the solution, the W string has to begin with a because the third symbol is A here. So, either it can continue with this or it can continue with this, but it cannot continue with this because if you take A here, then the fourth symbol will be a and the fourth symbol will become a B here. So, the solution cannot be continued with this. So, it has to follow this one. So, continuing the solution with 1, you get this. Now, the two strings match up to this point, but the string X is longer by one symbol. Again the same situation occurs, you cannot continue the solution with 3, it has to continue with 1 only. Now, if it continues, again the same situation occurs and at no time the string W will become equal to the string X. So, for this instance of post correspondence problem, no solution exists. So, the question is, given an instance, this is the problem. Given an instance of PCP, does it have a solution? This is the question. Okay. This is not decidable, and how do we prove that this is not decidable? Before going into that, we define a modified version of a PCP, an instance of modified post correspondence problem is this. It has got again two lists, A with k strings, B with k strings over an alphabet with at least 2 elements. This instance of MPCP, you call it as an MPCP, has a solution if there is a sequence of integers 1 I1 I2 IM such that W1 WI1 WI2 WIM is equal to X1 XI1 XI2 XI. So, you modify the PCP a little bit. Modified PCP has again two lists with k strings each, and this modified PCP has a solution if you can find a sequence of integers 1 I1 I2 IM such that W1 WI1 WI2 WIM is equal to X1 XI1 XIM. The difference between PCP and modified PCP is that the first string is fixed. The solution where you start, you have to start with W1 and X1, that is fixed. Then you can continue the solution. That is not there in PCP. Actually, it is not very much different because you can convert one instance of MPCP into PCP. That is what we will see next. What we prove is, if PCP were decidable, then MPCP would be decidable. We will prove this. You prove this is a lemma. If you can solve PCP, you can solve MPCP. This is a lemma. Or in other words, you are reducing MPCP to PCP. This is how you say, you are reducing MPCP to PCP. Now, in order the difference between them is that the first string is fixed in MPCP. You have to start the solution with W1 and X1. Then you have to find integers I1, I2, IM such that you get equal strings. Now, for every instance of MPCP, you construct an instance of PCP as follows. For every instance of MPCP, construct an instance of PCP as follows. Now, you have two lists A, B, W1, W2, WK, X1, X2, XK. Now, from this is the instance of MPCP. Now, from this you construct two lists C and D. The strings are Y0, Z0, Y1, Z1, YK, ZK, YK plus 1, ZK plus 1. If each list has k strings, here each list will have k plus 2 strings. Okay. and from this how do you get this, from this how do you get this, from this how do you get this. Then we will see what is y naught, what is yk plus 1. Now the alphabet is sigma, means here the alphabet is sigma union 2 more marker symbols, you have 2 more symbols which are used as markers. Now how do you get y1 from w1? Suppose w1, wi I will say wi is equal to some a1 a2 ar, then this implies yi will be a1 marker sign, a2 marker, ar marker. After every symbol use the marker. Okay. And if xi is b1 b2 bl say, then zi will be marker b1 marker b2 marker bl. Every symbol is preceded by the cent sign, marker sign. So for example, if I take this instance, if I want to form CD list, there are 3 strings in each list. Here there will be 3 plus 2, 5 strings. So the first one we will write later. Second one will be every symbol is followed by a cent sign here. Every symbol is preceded by the sign here. So it will be the first one, 0th one, we will see how it is. Cent 1, cent 0, cent 1. Okay. Second one will be 0 1 1. So 0 1 1, and here it will be 1 1. So 1 1. Third one will be 1 0 1 1 0 1 0 1 1. The last one is dollar here and cent dollar here. The first one, this is the same as this C1 C0 C1. Here this is preceded by a cent sign C1 C0 C. This is the same as this with 1 C added. Right. Let us write for here. The 0th one will be one is this one followed by the cent sign. Here it will be preceded by the cent sign. Here this each symbol will be followed by a cent sign. Here each will be preceded by a cent sign. Here each one will be followed by a cent sign. This will be preceded by a cent sign. The last one is dollar here and cent dollar here. Now you see that if the solution has to start, the first symbols are all different here. If the solution has to start, it has to start with 0. Look at it as a PCP. This is an instance of MPCP. So, if at all solution is there, it has to start with 1. If similarly here also. So, if the solution has to start, it has to start with this. It has to end with this. The last symbol here is sent, here it is some other symbol. So, if the solution has to end, it has to end with the 4, this one, right. So, in general what happens is, from 2 lists AB, you have formed 2 lists CD. Corresponding to W1 X1, you got Y1 Z1 by writing send sign after each symbol here and before each symbol there. And the YK plus 1 ZK plus 1 is dollar send dollar. Y0 and Z0 are such that Z0 and Z1 are the same, but Y0 is Y1 with one more send symbol in the beginning, right. If the solution has to, if you look at this as a PCP, this is MPCP, this is the PCP we have constructed. If you look at it as a PCP, then the solution has to start with 0 and end with k plus 1. So, it has to start with 0 and end with k plus 1, right. Now, if you find sequences such that 0, I1, I2, I3, Im k plus 1 is a solution here, can you have a solution for this MPCP? The first string alone you are considering with one additional C here, is not it. So, if it starts means the corresponding string is 1 really. Then for I1 again you choose the same I1, I2, Im. The last is to adjust the markers and have the dollar sign, is not it. So, if this is a solution, this is a solution for the MPCP, this will be a solution for the PCP. And if this is a solution for the PCP, this will be a solution for the MPCP. Okay. So, any instance of MPCP, you are able to, for any instance you are able to construct an instance of PCP such that the MPCP instance has a solution if and only if the PCP instance has a solution. So, given an MPCP instance, you can construct a PCP instance, right. And if PCP were decidable, you will be able to say yes or no. Then for the instance of MPCP also, you will be able to say yes or no. That is why you say, if PCP were decidable, then MPCP would be decidable, right. The next thing we have to prove is PCP, MPCP is not decidable. Or you say that if MPCP is decidable, then LU is recursive. Or the question, does M accept W is decidable? You will prove this. if MPCP were decidable, then the question, does M accept W, is decidable. But you know that this is not decidable, right. Therefore, MPCP is not decidable. Therefore, PCP is not decidable. Okay. So, you are reducing LU or this question, does M accept W, to MPCP, and you are already reduced MPCP to PCP. Okay. Now, how does the proof go? Given M and W, given a Turing machine M and a string W, you construct an instance of MPCP such that M accepts W if and only if this instance of MPCP has a solution. The proof goes like this: given M and W, you construct an instance of MPCP such that M accepts W if and only if that instance of MPCP has a solution. So, M is given by K sigma gamma delta Q naught blank F, say. Now, the alphabet for the MPCP alphabet will be gamma union K union the hash symbol, one more symbol. All tape symbols, states and hash symbol. That will be the alphabet for the MPCP. Now, the pairs we will not write 1, 2, 3, but we will write depending upon the mapping of M. So, we will divide them into group. Initial MPCP means the first one has to be mentioned, initial one, first one, which how you have to start the solution, right. The solution will be hash Q naught W hash, just hash here. Q naught W is the initial ID. If you remember, for W when you want to start, what is the ID, initial ID? Q naught W. So, that the initial ID is put between hash, 2 hashes, and first this pair is just hash. Then you have some pairs. Group 1 will be you have X here, where X belongs to gamma, and then you can have hash or hash also, but not the states. Group 2 is to simulate the Turing machine. In Turing machine, you can have left moves, you can have right moves, and we have to distinguish 2 cases in the right moves. One is when you read a symbol, one when you read a first blank. So, tape may be like this. This is the non-blank, this is the first blank, this is the non-blank portion. You may be reading a symbol in state Q, or I will use the symbol X, okay. Or you may be reading this first blank symbol, first blank symbol. You have to distinguish between these two cases, right. Now, if delta of Qx is equal to Pyr, this could be the move. Then you have the pair Qx Yp. For this, you have the pair Qx Yp. And you can also have the move delta of Qx is equal to Pyl, left move. For this, the corresponding pair will be Zqx and Pzy. Where what is Z? Z can be any symbol. Z belongs to gamma. Any symbol, it can be any symbol. So, for each symbol you will have a pair, okay. For each symbol Z you will have a pair. Here right move, for one mapping you have only one pair. For left mapping, for each symbol of gamma you have a pair. There will be several pairs like that, okay. Then the blank symbol, if it is reading this position, if it is reading this first blank symbol, okay, then delta of Q blank is equal to P y r. It could be, the mapping can be like this. It can print a y here and then move right, that is possible. In that case, the pair will be Q hash is y p hash. It is printing y and moving right. You can also have delta of Q blank equal to P y L. It can be a move. What it does, it prints a y and moves left in state P, right. Here again, for each symbol of gamma you will have a pair. So, it will be Z Q hash, right. Then it prints a y but moves left and it will read a Z in P. This is for each Z. So, if it is a left move, there will be several pairs or pairs equal to the number of symbols in gamma. Right move there is only one pair. Okay. So, these are the pairs which you write for the moves of the Turing machine. Given W and M, you have to write the two lists A and B. And the first, because it is MPCP, the first pair you have to specify, this is the first. Then for any symbol in gamma, you have XX hash hash, and then simulating the moves you have this. Then once it accepts, it will accept in a final state. That is the third pair. If Q belongs to F, once you reach the final state, the pairs you have will be X, Q, Y, Q. You start consuming the symbols actually. So, X, Q is Q, Q, Y, Q. This is for consuming the symbols. The last pair will be Q hash hash hash. The proof is like this. You start the solution initially like this, start Q naught W, is not it? The solution will start like this. Now, you have to pick pairs such that you get Q naught W and hash here, right. You have to pick the pairs, but the pairs have been written in such a way that they are simulating the moves of the Turing machine. If Q of X is reading, X is being read in state Q, the next instance Y is printed and the state changes to P and it is moving right. So, in the ID, if you have Qx something, the next instance what will happen? This portion will remain as it is and this portion also will remain as it is, X changes to Y and Q changes to P. This will be the next ID. So, this is changed into this. And similarly for left move, suppose you have this and you have a symbol Z here, the next instance it will change to P, Z will be read, this will be changed to Y, is not it? So, this is the pair you are getting. So, while you try to fill this portion with Q naught W this, the next ID will come here. And now you have to fill this with this string, this pair. Now, when you try to do this, the next ID 1, ID naught, this is ID naught, this is ID 1, ID 2 will come here. When you try to fill this with ID 1, right. Then next when you try to fill this with ID 2, you will get ID 3. This is Wx, the string W, this is the string W, this is the string X. This is such that this is a partial solution. You say it is a partial solution. If W is a prefix of X, W is a prefix of X. Now, you continue this solution this Wx, you continue the solution until you reach a final state. Then when you reach a final state, symbol by symbol you try to absorb. So, ultimately here you have a longer string, you have a shorter string here. So, step by step you do that and ultimately you will end up with equal strings. And these are defined, that consuming symbols is defined only when you reach a final state, right. So, only when you reach a final state, you will start consuming the symbols and you will end up with equal strings. So, in the proof you can use induction and say that Wx is a, at any stage Wx is a partial solution. That is the solution is of the form ID 0, ID 1, ID k minus 1, and here you will have the same thing plus ID k, right. And this, for this portion you can use induction, because initially you start with hash and hash q naught w hash, right, and then you proceed. Then once you reach the final state, you start consuming the symbols and it will be possible to end them. So, what is the solution you have got? You from given W and M, you have constructed an instance of MPCP, and if M accepts W, then this will have a solution. You go to a final state and then you will get equal strength. If M does not accept W, you will not go to a final state, you may halt. In that case again that consuming of symbols will not be possible, you will not get equal strings. If it gets into a loop, if M gets into a loop on W, this partial solution will keep on continuing and ultimately you will not reach a final state, it will go on and on and on. You will not be able to get equal strings. So, M accepts W if and only if this instance of MPC has a solution. Suppose MPCP is decidable, then what you can do is, suppose MPCP is decidable, then what you do is, given M and W, you construct an instance of MPCP and give it to the algorithm, it solves this. Okay, this will come out with the answer yes or no. If it is yes, then M accepts W. If it is no, M does not accept W. So, you are able to solve the problem, does M accept W, but you know that is already an undecidable, you know that it is undecidable. So, assuming that MPCP is decidable, you are arriving at a contradiction. Okay. So, but this problem, does M accept W, is undecidable. You know that it is undecidable. So, we are arriving at a contradiction. Therefore, MPC is undecidable. And earlier you have proved that if PCP were decidable, MPCP was decidable, but MPCP is not decidable. So, PCP is not decidable. Therefore, PCP is so we have reduced the problem does M accept W to MPCP, and we have reduced MPCP to PCP, right, and showing that all these problems are undecidable. Okay. So, we will take an example in the next class and also show how the problem whether a grammar, context free grammar is ambiguous or not is undecidable, making use of this. Okay.